In the previous video, we focused on how to evaluate a RAG system. We looked at how to measure retrieval quality, grounding quality, and system drift using matrices like recall at K, mean reciprocal rank, and faithfulness. One of the most common discoveries teams make after running that evaluation is that the retriever is the problem. In many real systems, recall is much lower than expected. The correct information exists in the knowledge base, but the retriever fails to bring it into the top results. When that happens, the language model never even sees the right evidence. And once that happens, no amount of prompting or model tuning can fix the answer. In this video, I'm going to walk through how I improved recall at 5 from 0.4 to 0.9 by only changing how knowledge is structured and retrieved. Let's start with the baseline. We run our evaluation set across multiple queries and measure recall at 5. The result is 0.4. This means that in 60% of the cases, the retriever fails to return the correct chunk in top 5 results. The knowledge is present, but it's not being found. This is a classic retrieval failure pattern, and it's very important to understand that if recall is 0 for a query, the model is forced to guess. Even a perfect model cannot generate a grounded answer if it never receives the right context. So improving recall becomes the single most important lever for improving RAG accuracy. In our case, the recall was very low, which is 0.4, and when the recall is low, the root cause is almost never one single issue. It's usually a combination of structural problems in how the data is prepared and indexed. In our case, the main issues were large chunk sizes, no overlap between chunks, and query phrasing that did not align well with how the documents were written. All three of these reduce the retriever's ability to find precise matches, and none of them have anything to do with the model. So we applied a few fixes. Fix 1 was focusing on smaller chunks. The improvement came from changing chunk size. Initially, the system was using large chunks, around 1000 tokens per chunk. Large chunk looks efficient, but they dilute signal. When a chunk contains too many topics, the embedding represents an average of everything inside it. This makes it harder for the retriever to match a specific question to a specific fact. So we reduced chunk size to around 300 tokens. Immediately, recall improved. Now, each chunk represented a more focused piece of information. Specific facts became easier to match. This alone pushed recall significantly higher. The second improvement was adding overlap between chunks. Without overlap, important facts often sit right at boundary between two chunks. If boundary cuts through a key sentence, neither chunk fully represents that information. The retriever then fails to match either chunk strongly. By introducing overlap, we ensure that important content appears in more than one chunk. This dramatically increases the probability that at least one of those chunks will be retrieved. After adding overlap, recall improved again. The third improvement that we made was query rewriting. Usually, users rarely ask questions in the same language used in documents. For example, a document may say initial public offering, while a user asks when did the company go public. These mean the same thing, but embeddings do not always treat them equally. So we added a small step where the system reformulates the user query into a more structured version. This makes the query more aligned with how information is written in the knowledge base. Once this was added, recall improved further. The final improvement that we made was reducing search space. Initially, the retriever searched across all documents, policies, reports, summaries, and unrelated material. That created so much noise. By adding lightweight filtering and narrowing the retrieval scope to relevant document types, the retriever had fewer distractions and high signal density. This made the ranking more accurate. After applying these changes together, recall at 5 increased from 0.4 to about 0.9. That means in 90% of cases, the correct chunk now appears in top 5 results. And the interesting part is that the only thing that changed was how knowledge was structured and retrieved. Once recall improved, grounding improved automatically. And once grounding improved, hallucination drops significantly. Now let's look at a code demo. Now I'm going to walk through the code at high level so you can see exactly how this demo is structured and how the evaluation is computed without getting lost in the implementation details. So at the top of the file, we have some standard import like scikit-learn and a few more libraries. The standard imports are just for basic text processing and typing and data structures. Then I import NumPy pandas. Next, I define the data models for the demo using data class. The first data class is document. It has stable document ID, doc ID, doc type, and full text. The next one is chunk. The chunk class represent a piece of document that will be indexed and retrieved later. It has a chunk ID, the parent document ID, and type and text as well. The next one is eval item. This represents one row in the evaluation set. This contains a query ID, the user query text, and the gold document ID where correct evidence lives, and a gold span, which is a literal phrase that must appear in supporting chunk. Then after the data classes, I define the build corpus function to build corpus that returns a small list of documents that I have created using the data class. They contain the real facts like IPO year, refund window, MFA requirement, SLO target, etc. And there are distractors documents designed to create noise. This is important because retrieval evaluation only becomes meaningful when the system has to rank relevant content above the non-relevant content. Next, I define build eval set. This is a set of queries we use to compute recall at K and the other matrices. Some queries match document language directly, and the others are phrased the way real users ask questions using synonyms and paraphrases. That mismatch between user language and document language is one of the most common reasons recall drops in production. Next, we move into chunking. Here's a tokenize function, which is a small helper function to tokenize for this demo. Then there is a chunking function that split each document into fixed size chunks with an optional overlap. This is the first lever we tune. Large document can dilute signal. Overlap helps prevent important facts from being lost at chunk boundaries. After that, we build retriever that trains TF-IDF vectorizer on the chunk text and build a chunk metric. Then retrieve function takes a query, vectorizer, and computes cosine similarity and return the top K chunks in ranked order along with similarity scores. There's also an optional filter which is allowed doc type that lets us restrict retriever to certain document types. This is the second lever we tune. Filtering reduces noise by shrinking the search space. Next is query rewriting, which is our third improvement. Rewrite query is intentionally deterministic. You can see it uses simple rewrite rules to convert user language into document aligned language. For example, go public is initial public offering IPO. Money back is refund window. Two-factor authentication becomes multi-factor authentication MFA, and so on. In real system, rewriting can be LLM based, but for a demo, this is a better approach because it is reproducible and you can see exactly what's changing. Now we get to the evaluation metrics. First one is find relevant chunks. That looks at chunks from the gold document and identifies which chunks contain the gold span. That gives us a set of chunk IDs that count as correct evidence for that particular query. Then recall at K checks whether any relevant chunk appears in the retrieved top K list. MMR checks how early the first relevant chunk appears, and precision at K computes how many of the retrieved chunks are relevant divided by K. Now we get to the evaluation runner. Evaluate config is the core function that runs the whole evaluation end to end for one configuration. It builds chunks using the current chunk size and overlap. It builds the retriever. Then for each query, it optionally rewrites the query, runs retrieval, computes relevant chunks, and computes the matrices. The function returns a data frame with per query results so we can inspect misses and not just look at an average. Then there is a print function here, which is also a helper function that prints averages for recall, MRR, and precision, and it prints any misses where recall is 0. That is useful because you always want to know which queries failed. Finally, we get to the main class. The main build corpus and then build evaluation sets. Then runs the evaluation 3 times. The first one is baseline, where we have large chunks, no overlap, no rewriting, and no filtering. The second one is improved chunking, where we have smaller chunks with overlaps, still no rewriting and filtering. The third run is optimized one, which keeps the improved chunking. And then we add query rewriting and filtering to remove distracted document types. And then we print the results. So we now run it and see how it improves the recall at K. I just finished running it, and let's walk through the results from the 3 configurations and understand what actually changed. We start with the baseline setup. In the baseline configuration, we are using large chunks, no overlap and no filtering or rewriting. So this represents a simple first version of RAG system where the documents are indexed and searched as is. Looking at the metrics, we can see that the recall at 5 is 1. Which means that we are finding the right information. However, recall alone doesn't tell us how well the system is ranking results. If we look at the MRR, it is 0.67. This tells us on average the correct chunk is not always appearing at the very top. Sometimes it is first, sometimes second, and sometimes third. Precision at 5 is 0.20, which means on average only 1 out of 5 retrieved chunks is actually relevant, and remaining 4 are noise. There are also no misses reported in this case. Now we move to the second configuration, which is using smaller chunks with overlap. Here recall at 5 is still 1.0. So the system was already finding the correct chunk before. The chunking alone did not change. MRR also remains around 0.67 again. This tells us while chunking can help in many cases, in this particular data set, it did not significantly improve ranking position. Precision at 5 is a 0.20 again, which is typically one of them is true match. Now we look at the third one, which is optimized configuration. This setup uses improved chunking plus the query rewriting and light filtering. Recall at 5 is 1.0, which is expected. But now we see a clearer change in MRR, which is now 0.92. It's an important improvement. It means the correct chunk is now appearing much earlier in the ranking, often in the first position rather than the second or third. So even though recall did not change, the retriever became significantly better at prioritizing the right information. Precision at 5 remains 0.20, which is expected because we are still returning 5 chunks, 5 results, but the key difference is that the most relevant chunk is now much more likely to be at the top. Now we look at the comparison table here. All 3 configurations show recall at 1.0, which tells us the retriever was already capable of finding the information, but the ranking quality improved significantly in the optimized setup, which is reflected in MRR moving from 0.6 to 0.92, which is an important insight. Sometimes the problem is not just the system cannot find the correct evidence. Sometimes the problem is that it doesn't rank that evidence highly enough. And when the correct chunk is ranked lower, it might not make it to the context window in real production systems, especially with the tighter token limits. So in this case, the optimization did not increase recall. It improves how early the correct information appears. That's all I wanted to cover in this video.